right, so let's dive deeper into change in enthalpy or delta H, right? And let's start applying it to actual like chemical reactions, kind of doing calculations with delta H, calculating delta H, all of that business. So just to kind of put into context, right, what exactly change in enthalpy means for chemical reactions, right, specifically. So if we think of like any change as being the difference between like the final and the initial, right, we could interpret delta H like so, where we initially have reactants and we finally have products. So your change in enthalpy is equal to the enthalpy of the products minus the enthalpy of the reactants. And so, right, if we think about like how much thermal energy the reactants have versus how much the products have, right, that can kind of give us some insight into like the sign of the change in enthalpy, right, whether that's a positive or a negative value. So just to kind of get us started here, right, let's think about this question. If the change in enthalpy for a reaction is negative, did the reactants release energy or absorb energy? Right, so again, thinking about like the sign of different changes in energy, whether that's like a positive or negative value, right, go ahead and kind of think through this question, right, if delta H is negative, do the reactants release energy or absorb energy? Right, so in this example, the reactants released energy. That's what's going to make delta H negative, right? If delta H is a negative value, then what that means is that the enthalpy of the products is a lower amount than the enthalpy of the reactants. The reactants started at a higher energy level and then went down to a lower state when they turned into products. What that also means then, right, is that that energy that's been released, right, that is heat that's being produced there, right? So again, enthalpy is kind of used interchangeably with heat, and generally, right, the energy that we consider is mostly enthalpy. So, right, in a way, in this chemical reaction, we have not just like products being made, but we also have heat being produced with that. So let's look at some more examples kind of similar to this, right? So this is an example of an exothermic process where you have thermal energy, heat, exiting from your system, right? So exothermic, kind of thinking about it being released. In a sense, then, heat is another product that's being produced from this chemical reaction. So a good example of this that you may have come across in your own life are little chemical hand warmers like these ones. So these work by oxidizing iron into iron 3 oxide, right, or Fe2O3. And that reaction is an exothermic reaction. So heat is being produced, and that's how the hand warmer gets hot, right? It is releasing heat as a result of this chemical reaction. Now, not all chemical reactions are exothermic, right? We can also have what are called endothermic processes, and in these scenarios, it's kind of the opposite effect, right? It's as if heat is a reactant. The way I think about this is like heat is entering the system, right? Endo as in enter. And so an example of an endothermic process that, again, you may have seen before are chemical cold packs. So these are really handy if you have like a first aid kit or something like that, where maybe you want a cold pack, but you can't necessarily have a freezer available. So these work by basically having like a little packet of solid ammonium nitrate. You break open that packet and there's water in the rest of the pack. That water then dissolves the ammonium nitrate, dissociating it into ammonium and nitrate ions, and in order to do that, it also requires heat as a reactant. And so, right, kind of writing out our chemical equations for both of these, right, I include heat as either a product for exothermic reactions or a reactant for endothermic reactions. And so, right, tying this back to the previous slide and that example, right, where delta H was a negative value, that was when heat was being released, right? And so that was, again, an exothermic process. And so, right, we can actually kind of tie delta H as a number to a reaction like so. So, right, again, looking at our exothermic hand warmer example here, the enthalpy change of reaction, or delta H reaction, is equal to negative 1,648 kilojoules per mole. So right, just to get a little bit more specific here, that delta H reaction, or delta H RXN for short, that's the heat that's released or absorbed per every mole of the reaction. So what I mean by that is like when 4 moles of iron and 3 moles of oxygen gas react to form 2 moles of iron 3 oxide, right, that releases 1,648 kilojoules. So, right, the negative sign there implies that loss, that release of heat, and that kilojoule per mole unit that we use is not per mole of iron per se, it's per mole of the entire reaction occurring. So, right, we'll kind of look at some examples in a minute and look further into that. But so, right, compare that again to the endothermic cold packs, where it has a delta H of reaction of 25.7 kilojoules per mole. Now, oftentimes, just to be like a little extra and a little bit more clear about whether a reaction is endo or exothermic, right, I'll include the positive sign when I'm talking about an endothermic reaction, just to be very clear that like heat is being absorbed as a result of this process, right? So that positive value there indicates that we have an endothermic reaction. Now to kind of apply our delta H reaction values, so right, let's look at this example with our hand warmers, right? So one hand warmer contains 350 milligrams of iron. But so then what would be the heat, say in kilojoules, of that one hand warmer completely reacting? So I think about how you might maybe set this up as like conversion factors, right? Looking at our enthalpy of reaction up above, again, that enthalpy of reaction is per mole of the entire reaction, so keep that in mind. But it gives us your best shot, and then we'll kind of go over it in the next slide. All right, so for this one, I mean, mathematically, it may be a little tricky. Again, we'll walk through the solution in just a couple of slides. But right, just right off the bat, I can at least eliminate one of these options. So right, thinking just generally and like in context here, right, the heat of the hand warmer should be a negative value. Because the hand warmer itself is releasing heat, right, that loss of heat is a negative value with that. So I can immediately get rid of choice C here. It's not going to be a positive 2.6 kilojoules. That wouldn't quite work out. But right, actually solving for this one, I do get negative 2.6 kilojoules. So let's kind of walk through why that is, and we'll see exactly how we can arrive at this answer. So right, in terms of working our delta H reaction into, say, our different conversion factor problems and things like that, we can think of that delta H as kind of just another mole ratio. So what I mean here is like taking our molar coefficients from the balanced equation and kind of relating that to delta H reaction. Again, right, that negative 1,648 kilojoules, that's per mole of the entire reaction. So that's per 4 moles of iron, or per 3 moles of O2, or per 2 moles of Fe2O3, right? So I have all of these potential conversion factors kind of included in my delta H here. And as always the case, right, any conversion factor can be flipped around to its reciprocal. And so, right, we can also have all of the inverses of these as well. But so kind of applying that then, right, back to our earlier question of what is the heat in kilojoules of one hand warmer completely reacting, right? If I set this up as a conversion factor problem, I'm beginning with 350 milligrams of iron, and I want to turn that into kilojoules. So right, I would set up my conversion factors like so. The first conversion that I might make is taking care of those milligrams, right? And so I know that 1 gram is 1,000 milligrams, so I can set up that first conversion. From there, I can go from grams to moles using the molar mass of iron, which taken from the periodic table is just 55.85 grams per mole. Sorry, if I'm trying to cancel out those grams, I have grams on the bottom, moles on top. Now, because I have moles of iron, I'm going to use that conversion factor of delta H over 4 moles of Fe, right? So negative 1,648 kilojoules per 4 moles of iron. And so solving for that, I get negative 2.6 kilojoules. Again, this should be a negative value because we are losing heat from our hand warmer there. All right, so let's look at another example, right? This time, again, looking at the endothermic cold packs, which again, I have the reaction written out up above and the enthalpy of reaction included. By the way, this whole setup, having the chemical equation with delta H included, that's referred to as a thermochemical equation, right? It's just involving the thermo of it, the heat involved with that reaction. But so anyway, just kind of an aside there, right, let's look at this example where I have a sample of ammonium nitrate dissolving, which absorbs 15.4 kilojoules of heat. So my question here is, how many grams did that ammonium nitrate sample weigh? But so right, this is kind of the opposite version of our last example, right? Go ahead and try to set this one up. Again, think of it as a conversion factor problem, maybe starting with your 15.4 kilojoules. How can you then convert that into grams of ammonium nitrate? So go ahead and take a moment on that, and then we'll go over it in a little bit. All right, so setting this one up, right, again, I'm trying to convert my 15.4 kilojoules into grams of ammonium nitrate, or NH4NO3. So beginning with kilojoules, right, I may try to first convert that into moles. Now, what kind of moles should I convert to? Because if I look at my delta H reaction, right, that's just kilojoules per mole. It's very generic. That could be per mole of ammonium nitrate, per mole of ammonium ion, per mole of nitrate ion, right? There's a whole bunch of different options there. Now, because my answer should be in grams of ammonium nitrate, right, I should probably link that first to the moles of ammonium nitrate. And so I can do that like so, right? I see from my chemical equation that there is 1 as my molar coefficient of NH4NO3. And so what that means then is that for 1 mole of NH4NO3, 25.7 kilojoules are associated with that. And then from there, right, I have moles of ammonium nitrate. I can turn that into grams of ammonium nitrate just using its molar mass, which I calculated as 80.06 grams per mole. And so now my conversion factors are all set up. I can evaluate this out, and I got 48.0 grams of NH4NO3. Again, just kind of keeping track of sig figs and things. I know that this should be 3 sig figs because the 15.4 kilojoules was 3 sig figs. The 25.7 kilojoules per mole was also 3 sig figs. That's going to count towards our sig fig amounts. And so, right, out of all the different measured values that we have here, 3 is kind of our limiting sig fig number. But so that's it for this video. Please let me know if you have any questions, and I'm always happy to help.